Okay, so since this assignment involves a lot of conditional expectation, so let us warm up a little bit. So this is a warm-up question. So suppose z is a random variable f of x1 to xn, where x1 to xn may or may not be independent, and this is our notation, the standard notation from the lecture. And so the question is, yeah, I mean, which of these options are correct? So these are just a few properties. So for instance, if you consider option A, this is expectation of z given the first k minus 1 variables, and on the right we have uh, expectation of z given, right, that kind of thing. So this is this property that if we want to compute expectation of z given x, this is same as if we take expectation of um, yeah, so suppose expectation of z given xy. Okay, so this is something like, okay, on the left hand side you are given x and you compute the expectation of z given x. So what is your best estimate of z? Here you compute expectation of z given x, but then you have, but if you are given both x and y, since this does not depend on y anymore, I mean directly, so this is just expectation of z given x, right? So that is what we have. So this is basically f. This will be some function h of x, expectation of z given x. So this is asking like, what is this h of x given x y? So you want to compute a function of x, and you're given both x and y. So this would just be h of x, right? So right, and this h of x is like, yeah. So that is why the first option is correct. The second option, this is what is known as tower property of conditional expectation, which is that expectation of z given x. This is same as you can come down. I mean, you can come to expectation of z given x in stepwise manner. So you can first compute expectation of z given xy for any y, and then of this function you can compute expectation of z given x. So this is a tower property that you're descending. You're first computing z when you both know x and y, and now this is some function, say h of x comma y, right? And now you compute again given x, what would be the best approximation of h of x comma y, and that would be expectation of z given x. So again, so B is also correct. And then option C. So option C would be a special case of this tower property. So special case of tower property is what? If you have expectation of z given x, and you want to descend further, so you just take expectation. Okay, so this would just be expectation of z. Okay, so this is what option C. So option C, LHS would just be expectation of z, and RHS would also just be expectation of z. Right? It doesn't matter what conditioning you took earlier because you took one more expectation outside these expectations, and so this C is also correct. And D is same as C, but it says only if x1 to xn are independent. So this is not correct. I mean, if it was if, then it would have been correct, but since it's only if, we don't. Yeah, this is. So this covers most of the useful properties of this conditional expectation. One is this descending thing where you condition on more and then condition on less. Other thing is ascending kind of thing where you condition on less and then condition on more. So once you condition on less, you have lost that information. So conditioning on more will not give you anything else. So it would just remain expectation of z given x. Uh, these are ascending descending properties, and yeah, these are the main properties. And then the next question will consider one more property, which was used in the derivation of Efronstein, which uses the fact that x1 to xn are independent. So again, this is the same setting as before, but here again may or may not be independent. So which of these is correct? So expectation of z given xk minus 1. Okay, and here first you are given xn and then you come to xk minus 1. So since this xn, it xk minus 1 is a subset of xn, so this is again by toggle property, this would be correct. Because you are conditioning on more and then conditioning on less. Then B is same as A, but here we have like if x1 to xn are independent, so this is also true if they are independent. I mean, this is true both if they are independent and not independent. And then we have this important property or a useful property, which is that expectation of z given xk minus 1. Okay. On the right, we have expectation of z given everything except xk. So this is xk minus 1. Okay, and xk plus 1. Okay. So basically, we are ignoring xk. And then we bring back xk here while ignoring xk plus 1 now. So this doesn't exactly follow from the tower property uh, because left this thing is not a subset of this, right? Because right, so we have like xk minus 1. So yeah, let me just fully write out what this is. So this is like x1 to xk minus 1 and then xk plus 1. First you condition on that, and then the condition is x1 to xk minus 1 and then xk. Okay, so first of all, we can't use tower property. I mean, this tower property setting is not valid because this is not true that the right hand side is a subset of this, because right hand side has xk whereas left has doesn't have xk. And similarly, this is also not true, so we can't use the ascending property as well. So here we have xk plus 1, but there is no xk k plus xk plus 1 here. So I mean, both are not subsets of each other, and so this is not true in general. But if x1 to xn are independent, okay, so basically this is what was discussed in the lecture. So this is like if you have expectation of z given some random variable a, okay, so this would be same as expectation of z given a comma b, which is, I mean, this is not true yet. So if we had taken one more expectation and then conditioned on a, then this would have been true, right? By this is by tower property. So first you condition on ab, then you condition on a, so you get a. But this says further that if a, b, c are independent, then this is also true. Okay, so you condition on a comma b, and then you condition on a comma c, where a, b, c are mutually independent. Okay, and why is this true? Suppose this is a function h which depends on a comma b, right? So you basically have expectation of h a comma b given a comma c, right? Uh, right, and where a, b, c are independent. So okay, okay, what is conditional expectation in general? It's like z given x. So this means that for every instance of x, say x equals to x, there will be a probability distribution, a conditional probability distribution, right? So first I mean, to begin with, you had like one big probability distribution over the entire sample space. Now you are given x equals x, so you condition on that x equals x, and now according to this distribution, compute the expectation of z, right? So compute uh, expectation of z with respect to this distribution. In essence, whatever you're given, fix that and condition on that, average with other random variables, all the other random variables, average it out. So here we have like h a comma b, uh, right? And so and here we are given h a comma c. So what would be a conditional distribution? A conditional distribution would be that You take expectation of h a comma b with respect to this conditional distribution where a equals a and c equals c, right? Uh, so that would be this expectation for a given instance of a comma c. Uh, versus now since versus what if you condition with just this a equals a, right? So suppose you condition given a, right? So we basically we want to compare, these two quantities. So we so okay, so here you take averaging with respect where a is equal to a, right? And since a and c are independent, what happens is that uh, these two probability distributions will be the same, right? And this is basically what we mean by independence. So suppose we are given x comma y, then probability, I mean we say x and y are independent if and only if what happens that probability of some x equals, right? This is the condition for independence, which is basically the same as like if you multiply on RHS and LHS by py, you get that px comma y is equal to px into py, right? So this is independence. So basically what this means is that probability of x, probability of x, so you have some probability of x, and probability of x given y, once you're given y, since they are independent, the probability of x doesn't change. So that is how we say that x and y are independent. So similarly here we have like we are given both a and c, and here we are just given a, and like both are independent. Um, so a and c are independent, so these two conditional probabilities would be exactly the same, right? So which means that h in this case, given a, is same as h of a comma b given a comma c, right? And we know what h of a comma b is. It's like expectation of z given a comma b, right? And so on the left hand side you have this standard property, now tower property, that you're given a comma b, then you're just given a, so it would be expectation of z given a. And on the right hand side you have expectation of z given a comma b, which is this h, and then expectation of a comma c, so which is exactly this property here, right? And okay, so we just, it seems like we just use independence of a and c, but why independence of b as well? Because this probability distribution here where I put a dot, that would be that would involve b basically, that what is the probability that b equal b given a equal to a, and what is the probability that b equal to b given a and c. So right, since all these quantities are independent, we have that probability of b given a same as probability of b given a comma c. So I mean your expected your I mean possibility of b remains same whether you're given only a versus you're given both a and c, because b is independent of both, a and c. So yeah, so this is how basically we understand it. So this c is not correct, but yeah, but d is correct. And yeah, so this is the important, circle this part, which is like, yeah, so I mean you can, conditioning on only a would have been okay, but you are conditioning on both a and c now, so and independence allows you to do that. Okay, so now yeah, let's come to the assignment. So assignment, yeah, so this is a function, this would be some function of xk, and this would be again some function, some other function, say h1 xk minus 1, right? So basically once you are given xk, uh, it would remain the same, whatever this is. So like expectation of fx given x. So since you're given x, there is nothing else, right? So it's like f of x, right? So basically what we are doing is we are averaging with conditional probability where x equals x. And now what we are asking is what is the probability that x equals x given x equals x? So that probability would be, yeah, just 1. So this expectation basically is same as f of x. Okay. So similarly, this entire thing is a function of xk. I mean, this is xk minus 1, that is okay. And you're given xk, so you don't need to do anything else. So the same quantity will be retained. So yeah, this is problem 1. 0 is incorrect. This D would be a deterministic quantity. In C, undefined. Yeah, undefined is also not correct. So yeah. Okay. So in the previous question, what would be variance of f of xn? Yeah, so we saw this, the variance in the Efronstein derivation. We saw that the variance would be, I mean, you break this random variable f of xn into various parts, right? F of xn, we write it as I equals or k equals 1 to n delta k. Okay, where delta k is what? It's like f of expected value of f of xn given xk, x power k, minus expectation of f of xn given xk minus 1. So for k equals 1, what k minus 1 is, like you're given nothing, so it would just be plain expectation. Yeah, so this quantity is actually f of xn minus expected value of f of xn. Okay. And we broke this random variable into this LHS into n parts. And then, yeah, and then we proved that these random variables are uncorrelated, which means that expected value of delta I, delta j is same as expected value of delta I into expected value of delta j. And we proved that this is 0, and so yeah, so uncorrelated means expectation of delta j is 0. And this derivation did not involve any use of independence at all. Like this did not require any assumption. So right, so if we want to show this, what we have is, so let me just write in terms of z. We have z given xi minus z given xi minus 1. So this was delta I. And then x given z given xj minus z given xj minus 1. Okay, and so here we use one trick. So we assumed first of all that I is less than j, right, without loss of generality. We assume this, and then if you have an expectation of some quantity, say dot, this is same as expectation of dot given something, given x, say, right? This is our property. So we exploited this property here. So this this complete expectation, we first wrote it as an expectation of a conditional expectation, and how we did so, assuming I less than j. So we condition this whole quantity on x. What did you condition on? I think condition on xi, and then we took this entire expectation. Okay, so this doesn't change anything. You took some conditioning and then you took an expectation outside. So no, wait, is this correct? No, this is not. So yeah. So first you took this conditioning, right? So let me just draw this red bracket so we know what pairing. right? And then we again took this bigger bracket, so the total would just be this. So okay, so now you're so okay, again this is x power I. So suppose you're given x power I. Okay, so since you're given x power I, what you can do is that you can just take this part outside of the conditioning expectation, because since you're given x power, so since you're given x power I, and this is a function of x power I, so this basically becomes a constant inside this expectation. This becomes a constant, right? Because you are given x power I, and this is a function of x power I, so this becomes like a constant. And we know from the linearity property of expectation that we can pull constants outside, right? So we will pull this constant thing outside, which is like, and we are pulling it from this red bracket expectation. So xi minus z given xi minus 1. Okay, we pulled this outside. And then inside what we'll have remaining is this, again, this red thing. We'll have expectation of z given xj, expectation of z given xj minus 1, right? And this expectation given xi, okay, in this bracket. So, right, so and here we use, so okay, so first we use this property where, okay, since we are conditioning on xi and this is a function of xi, we took it outside because this acts just as a constant. And the next property we are going to use is the tower property. So we are assuming that I is less than j. So what will happen is that expectation of z given xj given xi, this would just be what? This would just be expectation of xi. Since I is less than j, we are descending. We first condition on more and now we are conditioning on less. So ultimately we'll have the lesser thing. And similarly the other thing, it would just be like z given xj minus 1 given xi, right? So this would again be, okay, so what did I write here? This would be z given xi. Okay, and this would again be like z given xi, right? Because j minus 1, it can be equal to I because I is less than j, so I can be j minus 1, but yeah. So, but this thing will be correct, still would be correct that you have. And so both these terms, when conditioned on this, become same, right? And so this term basically vanishes. This becomes 0, and so the entire thing becomes 0. And this is how we prove that that these deltas are uncorrelated. Okay, so the trick was that you have some multiplication of two things. So first we use that, okay, you have fx and gy, say given x, right? So this is, and then you had like one expectation outside, we won't. So what we first did was that since we are given x, we can just take, so fx acts as a constant for this conditional expectation, so it can just be taken outside, and we have like gy given x. And gy has this very specific property that, okay, you're conditioning on more, and both are conditioned on something which is less. So both will become equal when you condition on something which is less, and so it becomes like 0. Right, so this was the use, and nowhere did we use that xi's or xj's, they are independent. This is just like properties of conditional expectation. And so yeah, so under the assumption that they are uncorrelated, this would be true. Under the assumption they are zero mean ID, this would also be true. Under the assumption that marginal exists, this would be true. And yeah, so I mean, this is basically true no matter what assumption you take. This uncorrelatedness, this did not require independence. So even if you're working on a problem and x1 to xn are not independent, you can still use this uncorrelatedness and you can still relate the variance of this with to the sum of variances of this. Okay, and this would be like variance of fx minus expectation of nm, which is same as variance of f of xn, because adding or subtracting a constant does not affect the variance. Okay. So this was problem 2. Okay, so problem 3. Problem 3 is you have, and you can, you know that you can ask questions, right, if you want, like you don't have to wait till the end. Yeah, okay. So um
Uh, so actually, I'm not
hmm.
sure because haven't gone through like to clear my doubt. But the theory of this F1 can start with the properties of the bounded difference, and in that properties, I think they
No, no,
mentioned
so
that.
there was no bounded difference. So when we started this Stein, it was just that you have some function of a large number of random variables, and you want to compute the variance of that.
So basically, that function needs to be needs to have a bounded difference characteristic, or any kind of function will work.
No, any, and then bounded difference, we showed that okay, with bounded difference you can do something like that, would be a special case. So what we did was, so in Stein, okay, what was Stein? In Stein, we did something like this. We wrote that variance of this f of xn, okay, uh, where x1 to xn are independent. This was used at one step in the proof, not this uncorrelated step, but another step in the next step. So are independent. Okay, so in that case, what we have is this, that you basically break the variances into, we have variance, right, of f of xn. Okay, so what this means is just fix everything else except the kth variable, and then measure the variance with respect to that. So like you have like x1 to xn, uh, and somewhere xk. So just leave this variable, fix everything else, and you can fix to different values, right? And that is why we have this expectation outside, that okay, for one value of this x1 to xn, suppose x1 is 1, xn is like 2, xk is, you're leaving xk, considering as a function of x. Now suppose this happens with this, x1 equals 1, xn equals 2, happens with probability half. With other probability half, this is 2, this is 1, right? But again, you're leaving this as a variable. So take all the possible combinations, fix everything else, and just leave this as a variable, and that would be the variance. And then yeah, since you're taking all possible combination, take expectation. So this was Efrenstein, and this did not use any independence, or this only used independence. This did not use anything about like bounded, what is it, bounded difference property. And then we later showed that okay, once uh, using this we can show that okay, if f satisfies bounded difference property, if f satisfies like c1 to cn bounded difference property, in that case we can bound RHS uh, is less than equal to something, it's like ci square, I think 1 by 4, right? It may be 1 by 2, I don't know. So it's something, so I equals 1 to n, right? So this is a general formula, and
Only it's required the independence. There is no
yeah,
other thing
yeah,
required.
there's no other thing. So in general, if you want to compute uh, variance of a function of some quantity, so for instance, functions could be very complicated. In last assignment, we saw that bin packing problem, right? X1 to xn are sizes of items, and f is what is the minimum number of bins you can use. And so it becomes like very difficult to compute variance and things like that. So what you can do is that fix every other item and then just change one item. And for that case, things become very simple, right? It can vary only by one or things like that. So that is where reference time is used. That if you fix everything else, just change one, things suddenly become very easy. You can compute variance of that. And how do you relate that variance to the variance of the total function? So that is what reference time gives. And for bounded difference property, we can show further that this variance, once you fix one random variable, I mean, if you just leave the ith one unfixed, and fix everything else. And since they are it can change at most by ci, so the variance would be like approximately ci square. And so yeah, so that is how you get that. Okay, for bounded difference, this is like summation of ci square and by some constant. Okay. uh, so Efronstein is like in general very useful in equality for, and this is known as, okay, this you heard this term a lot. I mean, you hear this further, but yeah, it's something called tensorization. So tensorization is basically, if you want to compute something about a big random variable, and it depends on many constituent random variables like x1 to xn. Okay, what how to compute this quantity if you know results for only one variable. So right, so on the right hand side, you only need to know how to compute variance of one variable function, because you're fixing everything else, and using that thing you are able to compute this variance of n variable function. So this is, in general, this is known as tensorization. So this happens in like information theory as well. If you have xn, mutual information between xn and yn, this is like mutual information xi yi, right? I equals 1 to n if x and if independent. Right, so this is again tensorization, that you want to compute mutual information in n variables, and you know how to compute between one variable. So how do you relate these two quantities? So this is tensorization or chain rule, right? Things like that. So chain rule, yeah. Like in differentiation also, it's like when you're taking derivative, you need to know like how to compute derivative of one function. But then if you have like composition of functions, you can still compute derivative using derivative of, if you just know how to compute derivative of one function, right? So derivative of f into g is like derivative of f times derivative of g, I mean, into f. So this kind of thing. So if you have a machine which can compute only for one function, you can still use that machine to compute this thing. So this is like chain rule, and this is also like vaguely known as tensorization. Uh, yeah. So Efronstein is a general tensorization argument, and which allows us to relate variance of one variable to variance of n variables. And for bounded difference property, it's just a special thing that, okay, you can use it. So basically, we are using Efronstein uh, for concentration result, and how we know that we can bound RHS once we have this bounded difference property. So yeah, so bounded difference property is just an application of reference time. So yeah, so okay, so what this, okay, so with this one discuss this uncorrelatedness part, that you can break your random variable into like multiple random variables which are uncorrelated. Okay, and this did not require independence of x1 to xn. So this part you can do even if x1 to xn are not independent. Okay, so and now we have this instead of delta k, we have this delta tilde k, which is that you have f of xn, and you have like this quantity is, again we saw this quantity, this is same as x of minus k basically, which is that you're given everything except the kth variable. So we have this delta tilde, and okay, so we want to relate this to delta k. So what was delta k? Delta k is expected value of z given xk minus expected value of z given xk minus 1. Okay, this was delta k, and we saw that this, using that independence thing, we can write this thing as, okay, so what we want to do is we want to write everything in terms of like one expectation. So this can be written as z given xk minus 1 comma xk subscript k. Okay, and now if you wanted to use tower property, what we'll do is we'll just condition on xk minus 1 again, right? This would have been okay, but now what we are doing is we are taking something more. We are taking like xk plus 1 to xn, right? And since all of these are independent, so this is where independence is used. This is true. So this uses independence. This is the same thing we saw earlier, that expectation of z given a, same as expectation of z given ab. Okay, and then this would have been okay if we just had A, but now we'll have C, where C is independent of everything else. Okay, so this is the same property, uh, right? And so somehow the brackets are so yeah. Okay, there should be one more expectation. Okay. So this requires independence, and so what we have is that delta K is same as expectation of Z given xk minus expectation of Z given x uh, k given x of minus k. So this part is we only left out minus k, right? So this is what it is. Okay. And now we want to see which of these. Okay. So so this is true, but you can also do it like the other way. So if z of x given xk minus 1, again we are using that same thing, that ABC, but I just interchange the role of B and C. So it would just be like xk minus 1 and everything else. Okay, and then again we take one more expectation, and we have this xk minus 1 because xk minus 1 is here. Okay, and we also have this additional random xk, right? So this is true, but this the question requires something else. So it's basically expectation of z given xk minus expectation of z given x of minus k given x of k. Okay, comes from here, right? So I just interchange the role of B and C, and so now you have this common xk outside, and so you can write it as expectation of z minus expectation of z given x minus k given x of k. Okay, so since we have x of k common here, by linearity of independence. So okay, and this is just what was delta tilde k above, right? This is like where f is like z, right? And so we just showed that delta k is same as expected value of this delta tilde k given of xk, and we crucially use independence here to do this part here, this part. Okay, so A is true. This is xk minus 1, so this is not true. Here left hand side is a random variable, right hand side is a deterministic quantity, not true. And this not true in general. I mean, this requires independence, which was option A. Okay, so this is also not true. Okay, so this part uses independence. Okay, now okay. So in the previous question, what would be this variance of k f of xn? So if you fix the ks thing, what would be the variance of that? So what is this? What would be this variance k f of xn? This would be z, okay, minus expected value of z given everything else except k, right? Because if we are fixing the k, uh, this variance, okay, given the entire thing given x of minus k. So this is this variance. If you just write it out completely, that if you just fix everything except the kth quantity, in this case, so you have fixed everything except the kth quantity, so you have this large overall conditioning, and inside you have like z, okay, because you want expectation variance of f of xn, which is z, minus if you just take conditional expectation with minus k, okay, since we are fixing everything else. So this would be like conditional mean, So conditional variance, we are computing conditional variance basically. So conditional variance is like you have z minus conditional mean, the whole square, and overall given x minus k. So this is variance of k z. Okay, this is basically what that is, and that is why you had this extra expectation outside interference time, because this is still a random variable. It depends on this x minus k, and so you take extra expectation. So right, so okay, so we have this, and this we saw in the previous question. This quantity has been defined as delta tilde of k. Okay, the without the square. So this quantity, and so this is just expected value of delta tilde of k, the whole square, given x of minus k. Okay, and okay, and we use independence. Where did we use independence? We use independence. Yeah, where did we use independence? Yeah, for while deriving this delta tilde k, right? So I think we didn't use independence here at all, did we? So this is always true that variance with respect to the kth thing, you have this. Okay, I think this question is like there's a typo. I don't know if it's there in the thing as well, in the portal as well, but I think this should be like variance of f of x in. Okay, and this is less than equal to by Einstein we have like variance of k f of x in expected value k equal to n, right? And this is like we just derived here, that this is like delta k tilde the whole square given x of minus k. So right, um, so okay, basically B is correct. So this does not I think so. Even the question is like I the only thing is there should be no summation here. Why there is a summation, I don't understand. So if there is a k here, then there should not be a summation over k. So that is why I think that yeah, there is a typo. But if the question meant variance of the entire f, then it can only be true with inequality. Right? Efronstein is an inequality, it's not equality. So the question says what would be. So okay, so there are complications, right? So if you just remove this case, the B is correct. Uh, yeah, you need this conditioning, and so other options don't have it. So we'll just remove other options. But yeah, so I think that except that summation part, yeah. But otherwise, as the question is no option is correct if we also include the summation. You're right, and I think this part would be where we use independence. So okay, so again, what is the story so far? So we have like we wanted to compute variance of f of xn. Okay, using that uncorrelatedness, we broke it into things, and it was k delta k the whole square. Okay, and this is just the second moment because the mean of this is also 0 delta k. So right, so this comes from uncorrelatedness. This does not require independence. This is always true. Does not require independence. Okay, and then yeah, and then we have this thing we want to relate it to. This quantity is again, it's not an easy quantity. Delta k is what? It's like expectation of z given xk minus expectation of z given xk minus 1. Right? Not a very easy quantity, because again you're fixing only k quantities and other n minus k are still variable. Right? And so we wanted to relate it to a quantity which is in which only one thing is varying. So that is what delta tilde k was. It's like okay, you have like z minus expectation of z given everything except k, right? And right, so what was the previous question? Yeah, so whatever. So basically we want to relate this quantity to this quantity. So we have reached here, and now And now we use independence. Now use independence to relate it to this quantity, the delta tilde quantity, right? So that would basically give you that you have this delta k square, right? Okay, so let me not do this part. So okay, so what is this expectation of delta k square? It is expectation of z given xk minus expectation of z given xk minus 1, the whole square. Okay, and now we use the tilde property, the independence property, to write everything in terms of in something like this. So expected value of z of xk, which is okay. For xk minus 1, we'll write the x minus k, okay, and then we'll again take this and then write like xk, right? So this part was what? This is like xk minus 1 and then xk plus 1 to n. This part is what? This is xk minus 1 and xk. So again, xk minus 1 part thing is fixed here, and these two are, and right, these two are like disjoint and everything is independent. So only xk minus 1 will remain, like we saw earlier. So which this is the same as this, right? The whole square, uh, which is what? If we now we use something called Jensen's inequality, right? Which is true, which holds for conditional expectation as well. And it holds for conditional expectation as well because conditional expectation is also normal expectation, except that we fix some quantities and then we take expectation with respect to conditional probability, right? So we can bring this square inside. So, right, so basically we have that expectation of x, the whole square, is less than equal to expectation of x, the x square. And the conditional variant would be the expectation of x given y, the whole square, is less than equal to expectation of x square given y. This is a conditional instance. So we use this here, and what we get is like we get z. Okay, so we have this xk fixed. Both, we have xk in both, so that would come out, and it will have just z given x minus k the whole square, and then given xk, then this, right? And you have given xk, and then you have this one more expectation outside. So this would just give you that, yeah. So basically, you have related this to this. This is like this delta tilde k the whole square, right? So you had this, and then you use some independence, then use Jensen's to get this, and this inequality is by like Jensen's. And we also use independence. Okay, so B is correct, and yeah, everything else is incorrect. Okay, so this is basically the outline of the proof of Efronstein. That first break it into uncorrelated part, but this uncorrelated random variables, even though you're broken into many parts, these parts are still difficult to compute because you're fixing only k variables here. So now how do we relate it to a quantity where we fix only one, where we fix everything except one? That would be easy. I mean, if we could do that, and so we use independence there to relate it to this delta tilde k square, where we fix everything else except k, right? And that finally gave us reference time. Okay. Um, okay. So that was reference time. Reference time, yeah, very useful in general. Uh, so and now we have this, so this question. Yeah, I don't know why this question was asked, but I think this will be used somewhere in future lecture. So you have expectation of x into fx, and where x is the normal random variable. So what would be this? It would be like x fx to e power minus x square by 2 by root 2 pi dx. Okay, this is okay. And now we use we can use what can we use? What is that called? Integration by parts, right? So let me just write it like as thing, right? And we can use integration by part because this thing is easy to integrate. This we can integrate. we know that this is, if you just integrate it, it would be just e power x square by 2 by root 2 pi minus, right? Because if you differentiate this quantity, if you just differentiate, you get this, right? Differentiate and integration. So okay, so this part was easy. So now we use integration by part. So what is integration by? Integration part is that integral of one quantity to the other quantity is like write the first quantity as it is and integrate the second quantity, which is minus e power minus x square by 2 by root 2 pi. Okay, and take the limits of integration minus infinity to infinity. So everything is like minus infinity. Minus, okay, so take the derivative of the first part and again the integral of the second part, which is same as like minus or minus x square by 2 root 2 pi dx. Okay, and now this quantity here, this is 0 since f, so this is going to 0 at infinity and minus infinity, and f of x is also going to 0 at infinity minus infinity because it's like the thing with compact support. So compact support is like, yeah, supported on suppose an interval, that would be a compact support, bounded interval. And right, and this minus so becomes plus, so we just have like f dash x times e power minus x square by 2 by root 2 pi dx, which is same as this, just the expectation of f dash x. So for Gaussian, this is only true for Gaussian. So for Gaussian random variables, if you want to compute expected value of f dash x, it's same as computing expected value of x into fx, right? Now, so yeah, this is great. Okay, so yeah, this is the standard problem. So you have y1, y1 and y2 are both n01. Okay, so yeah, so y1 plus y2 has distributed. Okay, so any linear combination would also be Gaussian. So first option is not correct. Second option is correct. Yes, the second option can be a little confusing. It seems like, okay, y1 and y2 by 2 will be same as n01, but it has the same mean 0, but yeah, the variance gets, because sum of this is like the variance of y1 plus y2 would be 2, and since we have 1 by 2 here, that would multiply like 1 by 4 to the variance, and so 1 by 4 into 2 is half. So this is correct. Y1 square plus y2 square by 2 has exponential distribution. This is also correct. And root y1 square plus root y2 square has exponential. This is wrong. This is I think d. If you take square root of exponential, you get Rayleigh distribution or something. Yeah, I think it's Rayleigh distribution. Not sure. Okay, so B and C are correct. Okay, so this is this standard simple question, but yeah, we're building up to something, so that is why we have this question. Uh, okay, so that was one question. This question is again a separate thing. So you have a function which takes one value and outputs one value, and you have function g which takes two values and output one. And g is defined as this: take y1, y2. Okay, take y1 comma y2. You take two numbers. Then first compute this y1 square plus y2 square by 2. Okay, and now you can feed this to f because f takes one number, and so it would be y1 square plus y2 square by 2. Okay, this entire thing is g. So, and now question is, you want to compute the derivative of this, a gradient of this. So gradient of g would be what? It would be dou g dou y1, right? Y1 comma y2, and so yeah, let me just, since we already have y1 dou 1 and dou 2. So like first compute partial derivative with respect to the first variable, and then partial derivative with respect to the second variable of this g y1 comma y2, g y1 comma y2. Okay, and by chain rule, it's what would be the partial derivative? It would be just f dash of y1 square plus y2 square by 2. Okay, and now take derivative with respect to y1, so that would be 2y1 by 2 is just y1. And similarly, if you just do it with respect to the other thing as well, y2, right? And so you can take this f dash outside. So this is what option C is, f dash outside, and you just remain right. You just remain y1 comma y2. You're just left with y1 comma y2, and so yeah, so C is correct. Okay, this is just chain rule of derivatives. Okay, so yeah, so this was the problem for which we did question number 7 and 8. Um, so we derived something called Gaussian-Poincare inequality, right? Which was basically that if you want to compute the variance of fx, right, say xn, that is same as that is less than equal to expected value of gradient of fxn, right, the whole square, right? And this is, and we use Efronstein's to prove this, and you can see how Efronstein is coming into play here. What is gradient of f of xn? Gradient of f of xn is like derivative with respect to the first variable of f to derivative with respect to n variables. And when you take norm, what happens? You just square and right add everything. So derivative of the first square plus the derivative of the nth variable square. And now basically derivative with respect to 1 is measuring how much is f changing when you change just the first variable, keeping others fixed, right? Similarly, partial derivative with respect to n would be just fix n, no, just leave n as it is, but I mean fix everything except n,
Yeah,
yeah, and see what is the variation with respect to nth random variable, and just add all these things. So this is just like Efronstein inequality. And so Poincare inequality is this. Okay, so this is basically right. Okay, you want to compute the variance of the entire thing, compute the basically variation with respect to each quantity, and just take the expectation. So yeah, this is another way to another, yeah, manifestation of this Efronstein. And so you have Gaussian Poincare, and this question asks you to compute Poincare inequality for exponential. So suppose, uh, yeah, so what would be the thing for the exponential random variable, right? Um, yeah, I don't know what is again. I think this should be like f here, f of x. You want to compute variance of f of x. Uh, X is like a single. X belongs to real number. So 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 now this is the thing that you can write f of x as what? You can write it as f of these two are equal, y1 square plus y2 square by 2. Okay, these two are not equal. These two are equal in distribution, right? Where y1, y2 are normal random variables. X is exponential random variable. Okay, so these two quantities are equal in distribution. That f of x is same as f of y1 square plus y2 square in distribution. And yeah, since we are dealing only with expectations and variances, we need only be concerned about distributions. So yeah, okay. And now this can be seen as some function g of y1 comma y2, a two variable function, right? This, and for this quantity we know, so we want to compute variance of fx, which is same as variance of g of y1 comma y2, where y1 and y2 are normal, standard normal. And we for and we know that this would be less than expected value of gradient of g by Gaussian Efronstein, by Gaussian Poincare, right? We have already computed what was this thing. It was like f dash of y1 square plus y2 square by 2, since we have the square, it is square, times uh, y1 square plus y2 square, right? This is just what we computed earlier, right? And y1 square plus y2 square would be just 2 times y1 square by 2. So this is basically the same as expectation of 2 times f dash of x the whole square into x, where x is exponential. Okay, so yeah, so this D would be the correct answer. Okay, so again a typo here, that yeah, it should be variance of f of x. So
water is not water. It's okay.
hmm, Yeah, okay. So right, okay. So yeah, so this was the important thing to realize, that if you want to compute f of x and you can write that x as some function of Gaussian random variables, then you can use this Gaussian Poincare and get result for x. And yeah, finally. Fine, so this is one application of Efronstein, and this maybe I can cover this in the next session. But yeah, this kind of thing comes up in like applications as well. So you want to compute variance of z, which is this f of f function, and what you know is this, that for every you have this basically, there exists some function gi, which takes everything except the, I mean, where everything is fixed except the ith. No, yeah, we just remove the ith and everything else, right? This is like, yeah, x1 to xi minus 1, and then xi plus 1 to xn, right? So it takes n minus 1 things, right? And then we have this. And so which of the following are true? Okay, so we know that variance of z is less than equal to, so this is the usual reference time, that I equals 1 to n. Uh, Variance, just leave the ith one unfixed, and variance of z, right? That's it. Okay, and now what would this be like, variance of, so we know that variance of any random variable x, this is what, this is less than expected value of x minus a the whole square, right? And this holds for all a, right? This is true, and this reaches equality when a is equal to expectation of x, right? So if there is a random variable which varies between like 0 and between a and b, it is varying, like this can take any value here, and just fix any quantity between say x and y, just fix any quantity a here, and compute this random variable x minus a the whole square, take expectation. So variance would be less, variance would only be less than that. So variance is what is the optimal mean squared error, and that optimality is reached when a is equal to expectation of x. Okay, so this was for the usual one variable random variable. And again here we are considering, like, once you fix everything else, only the ith thing varies. So what happens here is that f of, you're computing this thing f of xn, right? uh, Minus this x minus, ideally you would have taken, so ideally you would have taken this expectation of z given this x minus I, right? You would have taken square of that, taken expectation, that would be, right, that would have been this quantity. So so the thing is that you can replace this quantity expectation of z given xi with any function of uh, x minus I, just like we could replace, so variance of x is expectation x minus expected x the whole square. We could replace this expectation of x with any number a, right? So similarly you can replace this expectation of z given x minus I with any function of x minus I, any deterministic function. Okay, any function which just takes x minus I, and just because this is also some function of x minus I, right? This is also, suppose, x of x minus I, and this is saying that you can replace it with any. So just replacing it with this gi's will give you that. And if you just take I over 1 to n, right? So replace with gi, basically replace with gi. So this won't give you the variance, but this gives you an upper bound on the variance. So for upper bound, right? And so this just becomes x minus gi of x minus I the whole square, right? You want to take expectation of that, and we'll give an x minus I, yeah, all that given everything. So basically we know that this is less than equal to f of x, this entire summation, this summation included. So this would just be less than f of x. Uh, yeah, f of x, and there is this expectation outside, right? So basically what we have shown is that the variance is less than expectation, right? Which is true for instance for Bernoulli random variables. For Bernoulli p, expectation is p, variance is like p into 1 minus p, right? So this happens to Bernoulli, but this is if you can find something which yeah, such that this condition is satisfied, right? So you again have this thing where variance is less than equal to expectation of z. So once this is true, b is also true because b is only weaker. A is always true no matter what, right? Variance of z is less than the second moment, and yeah, d is incorrect, right? So yeah, so I think this finishes this week's assignment. So yeah, any questions?
No.
No, okay. Yeah, so I think the next week's lecture it covers something called Herbst's argument. Okay, so so basically, I think you're realizing now that the thing is we want to bound this thing called log moment generating function, right? And that gives concentration results. And so even in this week 3 lectures which we discussed today, week 3, the last lecture, it uses this Efron-Stein inequality to bound moment generating function. So Efron-Stein is like for bounding variance, right? Bounding variance, and right, and if your random variable z is e power lambda by 2, say fx, right, minus expectation of fx. Suppose this is your random variable. Then when you compute variance, what happens? You take, right, it's like expectation of z square minus expectation of z the whole square. And when you take expectation of z square, what you get is just the usual e power lambda fx minus, right? You get this quantity. This is just moment generating an expectation of that. So this is moment generating function. And so this is why Efron-Stein is useful, that okay, even you're just computing variances, how do you use it to compute bounds on moment generating function? So this is how you define some random variable like this lambda by 2, and when you square it you get the usual moment generating function. And so you bound MGF using Efron-Stein. Okay, and then there is a convoluted way of doing it. So your MGF should satisfy some equation. Yeah, so I think you have to see the last. So your MGF satisfies some equation. So if MGF moment generating function. So moment generating function is what? It's a function, right, of g of lambda, suppose, uh, some function. If it's g of lambda satisfies some quantity, some expression, something like g of lambda by 2 is same as g dash of lambda, right? Some functional equation. Then you can bound g of lambda is less than equal to something lambda square, right? Something. Okay. Then so basically if your g of lambda satisfies this, then you can show that your MGF would be bounded. Basically, g of lambda would be bounded by something. And now to show this, if to this condition that g of lambda satisfies this condition, you use Efron-Stein to show this functional equation that g of lambda by 2 is something is related to g of lambda by some quantity, right? So this is not correct at all, but yeah, you can use Efron-Stein for this, right? And so this is how you get like bound on momentarity function using Efron-Stein. Uh, now in the next week, which is week 4, you'll use something called Herbst argument. So Herbst argument is again if g lambda satisfies something, then g lambda is less than equal to something, say lambda square b by 2. Right, where g lambda is again that moment generating thing. G of lambda is expectation of e power lambda z, suppose, right? So if g of lambda satisfies something, right, this happens. This is easy to show. I mean, in the lecture, this would be easy. This would be the easy part. So now the question becomes, can we prove this part that g of lambda satisfies that equation? For instance, like g of lambda by 2 is this. And for that we use we yeah, so we used Efronstein in this week's lecture, and which Efronstein was like variance of fz is less than equal to something. So tensorization of variance. Here we'll use tensorization of some other quantity, and that is called entropy, tensorization of entropy. Okay, this is not that entropy in the this is okay. This is related to that entropy which h of x, right, in information theory, but this is not exactly that same entropy. This is more related to the KL divergence. KL divergence is also known as entropy, relative entropy. So, right, so if g of lambda satisfies some condition, then g of lambda can be easily bounded. And this some condition, what is this some condition? That would be in terms of entropy. That I mean, you can derive that condition using tensorization of entropy instead of tensorization of variance. Okay, so that is this week's that would be this week's lecture, and even week 5 as well. That will also use this tensorization of entropy part. So tensorization of entropy is something which is very important for concentration inequalities in general. So yeah, so this tensorization of variance we saw in this lecture, tensorization of entropy would be next 2 weeks, and so that would cover the basic concentration courses. Like so that would be like all the basic toolkit you require, and then we'll see that how to derive these same like Azuma, what is it, McDermott's and all, using some other techniques. So like transportation method or something, right? So that would be like next week's. So so yeah, just go through those lectures, and if you have any questions, we can just discuss them next week. Okay.
Sure, sure,
Okay then.
sure. Thank you
Yeah.
so
Bye.
much.